Perfect. Okay, good afternoon. The last class, we saw what flexible manufacturing systems are, and also we analyzed their technological components. In addition, the term of variability was mentioned and its impact on the performance of the manufacturing system was discussed in the first classes of this course. So today we will discuss randomness, so the variability in flexible manufacturing systems. This is important because the higher variability is due to randomness, and we need to be able to quantify it and know its effect on the system's performance. The focus in this class is to provide insight into randomness and variability. We will define probability precisely in a precise way and define such concepts as independence, law of total probability, random variables, and others. We will introduce some widely used probability distribution for discrete and also for continuous random variables. Okay, since there is so much randomness in factory, this week we are going to cover some of the basics of probability. So I will start with a trick question for all of you. Suppose I flip a coin, as here in the video, and I flip this coin 100 times. And it comes up heads each of the 100 times. So what do you think? What is the probability that it will come up heads the next time? So some of you can answer that is 1/2 or the 50% of the time. True? That can be one answer. On the other hand, other people, other of you, can think the answer is almost certain to come out hits again. So the next, when I flip the coin again, I will have hits again the next time. Okay, yeah, some of you, Sergio, say that 50%, Juan Carlos also 50%. Yeah, but maybe one of you can think that if I flip the coin another time, I will obtain heads again because the 100 before times I flipped the coin, I obtained the head. So are two answers that all of you can have. So another way to ask the question is by asking how much you will be willing to bet that the next time will be heads. So suppose a lot of people is trying to enter. So suppose I say that if you bet on heads and it comes up heads, I will give you $1. If I told you it will be heads half the time, you will probably say you will bet less than $1. True? Because you want to gain money, not to lose money. So if I said it will almost certainly be heads, you will be willing to bet any amount more or less than $1, as you will be almost certainly get that dollar back no matter how much you bet. Okay, so because you have the certain that will be head. Half they are independent events, that is true. 50% throw are independents, that is true. Okay. So another way to talk about probability is to ask what betting odds would you require? And here is the answer about this question. Here is the answer in this slide, okay? So actually, the question was a little trick because I didn't explain the problem the problem fully. If your estimate was half the time you assumed the coin was fair, so it was perfect, since the outcome of each flip is independent of the outcome of previous flips, the probability is 1/2, okay? Because it's the same what you say, the flips are independent, okay? So if you do that, you treated this question as a probability problem. But if your estimate was that the next time you will obtain another time head, then you used the data provided to determine the probability of heads. Since we flipped the coin 100 times and you got heads each time. So if you say that the next time you will obtain head because you saw that the before times you obtained heads, you treated this question as a statistic problem. Probability and statistic are two different topics. Probability is a mathematical theory that describes uncertainty. It is the analysis of a random system and the prediction of their behavior. On the other hand, statistics are a set of techniques for extracting useful information from data. These techniques are generally divided using probability theory, but other techniques have recently emerged, as you can hear about machine learning or data analysis, and you can have the answer in a statistic way. Okay. So in this course, we make heavy use of probability and no statistics. Okay, in this course, we will use probability. So we will not use the information of the previous states. And this is not because statistics are not important to manufacturing system. Is important because now in nowadays, you can see that all the manufacturing process has sensors, and you with the data from the sensors, you can treat this in a statistic way. For example, using machine learning models, and you can predict what will be the probability of something. Okay, you can do it, and also here we will not use that because it's not important. In fact, it's very important, but it's because it's a lot of theory, and our time is not big, so we don't have a lot of time to explain both cases. So in this course, we will taking into account only probability. But what we understand by probability? So specifically, let's say I run an experiment that has possible outcomes. For example, outcome capital A, capital B, capital C, and other outcomes. What do you mean when I say that the probability of outcome capital A is P? So here we can have two main interpretations. The first one is a frequency interpretation, and the second one is the state of belief interpretation. In frequency interpretation, the probability that the result capital A is P means that if I perform the experiment many times, the fraction of times the result is capital A is close to capital P. And the more I do it, the closer is the fraction to capital P. This interpretation makes sense when considering an event that could occur many times or is highly refutable, okay? So let's see the next slide. And here we have the state of belief. In the state of belief interpretation, I am willing to base an action such as placing a bet or on opinion. For example, if I think the coin is fair, so if the coin is fair, I have the 1/2 probability that is head or is the other side. If I think the coin is fair, I am willing to bet less than $1 on heads if I get $1 if the outcomes is heads. An example of the state of belief interpretation is the choice of getting odds. So the statement that the probability that the result of an experiment is capital A is P, if before conducting the experiment, a risk-neutral observer will be willing to bet, for example, $1 against getting more than 1 minus capital P over P dollars. The reason for choosing that fraction is based on making sure that the expected value of the bet is positive, and we will discuss the expected values at the end of this class. Okay, so the idea here is that in the interpretation of probability, maybe we have information before to make the odds. Okay, so maybe we have a risk neutral observer and will be willing to bet $1 against getting more than 1 minus capital P over P dollar, for example. Also, maybe a better example will be betting on the outcome of an election. You cannot repeat a choice many times. You decide if you want to bet on the result based on your opinion about the effects of many influences. Okay, so you have a little information because you have many influences, and with that influences, you take a decision. Regardless of the interpretation we follow, we can formalize this with the axioms of probability. Then we can use these axioms to perform calculations on the results of complex systems. So here is why it's important to use the probability. While the probability may seem imprecise and uncertain phenomena, probability calculations are accurate and can model important real-world features very well. That is the important thing. We want to model the features. Remember that we are engineers, you will be engineers, and you want to take decision using quantities. Okay, so we can make calculations using this model that is a model about the features of our systems. And remember that the manufacturing systems are complex systems and has a lot of randomness. In this class, we will look at the fundamentals of probability theory. We will focus on those parts of the theory that will be useful to understand random events in factories and also their consequence. We will only see the surface of a lot of knowledge of probability theory. So we will see at the beginning some axioms, and the axioms of probability are very important because all quantitative probability methods are based on that. So it's important, if you know before in other course you learned about probability, in this course it's also important to remember that, because now we will use the probability to measure the behavior of our systems. Okay, now we will start with the probability axioms. And suppose we want to describe an experiment that has more than one outcome. We can define the universe, and here the universe is defined as capital U, and this is a set of all possible outcomes of the experiment, okay? The elements of U, the elements of all the possibles of the experiments are called samples. For example, here we have epsilon 1, epsilon 2, and these events are subsets of the universe capital U. Also, a special subset is a null or empty set if this is a set that has not elements, okay? So we can have a set that is zero or null or empty set, and this set maybe has not elements, okay? Here, capital P is a set of functions that has the following property. First, the probability of any subset epsilon sub index I is between 0 and 1. Okay, remember that we want to calculate the probability, and the probability goes from 0 to 1. In other words, from 0% to 100%. Okay, so this is the first axiom. The probability of the universe is 1 because it's the probability of all the subsets of our universe. So it's 1, the sum of all the events. The probability of the empty set is 0 because we don't have events, or is an empty set. And if epsilon 1 and epsilon 2 are disjoint, that is, the intersection is empty, they do not have samples in common. Then capital P of the union of epsilon subindex I and epsilon subindex J is equal to capital P of epsilon subindex A plus epsilon subindex J, the last formula here. Okay. So technically, capital P is a measure. We are obtaining a measure of something. We can think of a measure as a generalization of area or volume. If you think of the universe, if you think that the universe, for example, is a large patch of land, then some of the subsets, for example, the epsilon 1 or epsilon 2, we can think that are small patches of land within the universe. And here, the last two axioms are very natural. For example, the area of a set without land is 0. ¿Verdad? If we think that the universe is a land and small patches of land are the events, if the probability of this subset that is empty, so we don't have land, is 0. Okay, so it's a natural way to understand the behavior of the probability. And for example, in the last axiom, the area of a set of land consisting of two non-overlapping parcels is the sum of their areas. Okay, remember that I said that epsilon subindex I and subindex J are disjoint, so they don't have overlap. So it's natural way, if I have two lands separately, that if I want to know the probability, so it's the sum of both areas. Yeah, that is one way to think about probability. Now here we have some notations. For example, lowercase omega in the following slides, we will be the difference between lowercase and uppercase. Yeah, but lowercase omega is often used as a symbol for a generic sample, okay? Also, the subset of capital U are called events, and we saw it in the previous slide. We had some events. We saw that epsilon, we can call epsilon as events. We can see epsilon as events, and P of epsilon is the probability of an event, okay? So we have the event, the probability of event, the subsets of the universe are the events, and omega is often used as a symbol for a generic sample. Here we have some example to understand this. For example, you can, if you roll a single die, the possible outcomes are 1, 2, 3, 4, 5, and 6. Okay. So here, lowercase omega can be any of those values. Remember that lowercase omega is a generic sample. So if I throw a D and I can have 6 different values at the end, omega, lowercase omega can be any of those values. By other hand, if we translate this knowledge about probability to flexible manufacturing system, we can think that N of T is the number of parts in inventory at time T. So then we can have lowercase omega, and lowercase omega have some values that can be the number of parts, for example, in time 1, in time 2, in time 3, and so on. And this is also called sample path. So we can use probability in flexible manufacturing systems. So here's an example more related to manufacturing systems. And it's the same that I said before. So let's say that N of T is the number of parts in inventory at time T. So lowercase omega is a set of numbers N of 1, N of 2, and so on. And this is called sample root, or also is called sample path, okay? Also, an event can be defined by a declarations. For example, epsilon is the event that there are 6 parts in the buffer at time T equals 12. That, for example, here, omega, in a declaration, we can say that there are 6 parts in the buffer at time T equal to 12. The formal notation for this is the following. Here, this is a formal notation. So epsilon is a set of all lowercase omegas such that N of 12 is equal to 6. That is the formula way to make this declaration. And that is writing on the last line, which actually indicates the same thing here, this formula here at the end, okay? So, and you can see that it's the same. We will see that we can work in discrete sample space, or also we can work in continuous sample space. when we think about probability, because remember that we can have some values in a discrete way. So it's open or it's closed, or the machine is operating or the machine is off. So this can be a discrete sample space, but also we can work in a continuous space when we are measuring continuous values, for example, okay? Here we have an illustration of a discrete sample space. The circles represents, for example, the samples. The color of the circles indicates the probability. Now, if we imagine that we have a dart shooter that is throwing darts at this board, and the darts are going to land in the circles, in fact, let's make it interesting, and we think that the dart launcher is blindfolded, so he can see nothing. Now, the graphical notation here is that the darker circles represents higher probabilities and the lighter circles represent lower probabilities. So when the launcher throws his darts, we have more of them that tend to land in the darker circles because we have a high probability here, and fewer of them land in the lighter circles, okay? Because we have a low probability in the lighter circles. But we have to know, when we think about probability, that this is not uniform. And there is always a chance that we can get more in some of the lighter circles than in some of the darker ones. Okay, this is not uniform. Here we will talk about one type of diagrams that is useful for probability and to understand the behavior of different systems. Here we have the Venn diagram, and this diagram is useful for illustrating the set theory. And also, these Venn diagrams is useful to analyze complex systems as manufacturing systems. For example, here we can say that capital A is a subset of capital U. True? We have here this circle red is capital A, and we have capital U that is this block in yellow. For example, so we can say that capital A is an even. We can say that capital A is an even, and also we can have the notation capital A bar, this part of here. And this is a notation for the set of all elements that are not in capital A. Okay, so we have the universe, and here we have, for example, the even capital A, and all the elements that are not in capital A are part of capital A bar or capital bar A. Okay. Then, according to the last axiom of probability, capital P of capital bar A is equal to 1 minus P of capital A, okay? Because we have the universe and we are taking one part, and if the sum of both parts is equal to 1, the sum of the probability of capital A and the probability of capital A bar. So with mathematical, we can say that the probability of capital A bar is equal to 1 minus the probability of capital A. Yeah, but now we have to think what about two sets that have some elements in common. That probability is given by the formula shown here, this formula of here in the bottom part. And here we have to subtract the probability of the intersection to avoid counting that intersection twice. Okay, so we can see that this probability of A, capital A union capital B, we have these two events, is the probability of capital A plus the probability of capital B. But remember to not take into account this overlapping part 2 times or twice. We have to subtract the probability of this overlap. Okay, that is what we are doing here. Also, we can talk about independence. Independent events are those in which the occurrence of one has not effect on whether the other occurs. Therefore, the probability that both occurs is a product of each occurring. As we can see here, for example, the probability of capital A intersection capital B is equal to the probability of capital A multiplied by the probability of capital B, because both events are independent. So here we have an example. In this example, you can imagine that the dart launcher is throwing darts at the grid shown here in the bottom of the slide, this grid of here, the last one at the bottom. But you can see that the grid is divided in such a way that the upper left figure shows the probability of landing in vertical stripes. You can see this block of here, this grid of here, and the upper right corner, this part of here, shows the probability that the dart will land in horizontal stripes. But those two are independent of each other. So the probability that it will land on a square is a product of the probability that it will land on that horizontal strip and the probability that it will land on that vertical strip. For example, here we can see that the probability that if the dart go to this square up here, we can see that the probability of this stripe is this probability here, and the probability of this vertical stripe is this probability here. So the multiplication of both values is equal to this value. So that is the probability that the dart will go to this square. Yeah. But this is because both events are independent. This event of here and this event of here. Also, another important theory part about probability is the conditional probability. And this is a very important concept. If capital A and capital B are not independent, if capital A and capital B, remember, are not independent events, so it's not this case, then knowing that B has occurred affects the probability that A has occurred. Okay, and we can think this about machines. For example, if we have a line of continuous machines, if we know that one machine is stopped, maybe that information can help us to know if another machine need to stop because maybe don't have product to process, for example. Okay. So here, what is the probability that the dart will land on A, capital A, if I know that the dart has landed on capital B? For example, if we take the same example than that before. If capital B is a subset of capital A, the probability is 1. Okay. and that is true. If there is a large overlap between capital A and capital B, then that probability is high. On the other hand, if capital A and capital B are disjoint, in other words, they have not elements common, so we don't have the overlapping, then the probability is 0, okay? So the conditional probability is the probability that capital A has occurred since we know that capital B has occurred. In other words, for the dart to land on capital A, given that it has landed on capital B, it must land at the intersection of capital A and capital B. A given that it has landed on B is the probability of the intersection divided by the probability of B. So here we have this formula, and they say that the probability of A given B, capital B, is equal to the probability of capital A intersection capital B divided by the probability of capital B. Another way to write this is that the probability of the intersection of A with B is equal to the probability of A given B multiplied by the probability of capital B. So here we have an example about conditional probability. So now we can, for example, throw a die or roll a die, and let's call capital A the event of obtaining a number less than or equal to 3, okay? Capital A is the event of getting an odd number, okay? So we can have the number 1, we can have the number 3, and we can have the number 5. And capital B is the event of obtaining a number, no, it's the other way. Capital E is the event of getting an odd number, so 1, 3, 5, and B is the event of getting a number less than or equal to 3. So we can have 1, 2, or 3, okay? So the probability of capital A and the probability of capital B, they are both 1/2. ¿verdad? The probability of capital A and the probability of capital B, they are 1/2. So that is true because we have 2 events. So 1/2 to event A and the 1/2 to the other event B. Okay. The probability of capital A intersection capital B is just the probability of getting a 1 or 3. Okay, because the intersection between capital A and capital B is 1, and also the number 3, the number 2 and number 5 not. So the probability is equal to 1 divided by 3. Okay, so it's 1/5 because they are 2 chances. So the probability of capital A giving capital B is the probability of the intersection divided by the probability of capital B, which is equal to 2 divided by 3. Remember the formula. Remember this formula here of the last slide, and also we have here. We can say that the probability of A given B is equal to the probability of the intersection of both. So the intersection of both is equal to 1 divided by 3, and this is divided by the probability of B, and this is equal to 1/2. So in total, the probability of A given B is equal to 2 divided by 3. And one way to think about this is that the intercept is 1 or 3 and the probability of getting capital A is getting 1 or 3, but not 5. So that is equal to 2 divided by 3. Here we will talk about the law of total probability. The law of total probability addresses the following question. For example, suppose that the event capital A can occur in several different ways. Specifically, capital A could occur if epsilon 1 or epsilon 3 or epsilon 1, epsilon 2 or epsilon 3, and so on occurs. Okay? We know the probability of epsilon 1, epsilon 3, and epsilon 2 occurring, and we know the conditional probability that capital A occurs given that epsilon 1, epsilon 2, and so on has occurred. So the question is, what is the probability that capital A occurs? So let's take a look in this slide and just build this from simple cases to something more complicated. We can start, let be this set, let be this capital B, this set, which is the union of C and D. We can say that B is the union of C and B. And C and D, we can see that C and D are, for example, are disjoint. They are not overlapping. And that is, they do not have elements in common. In that case, the probability of capital A given capital C is the probability of an intersection with C divided by the probability of capital C. Remember the formula. So we have the probability of A given C is equal to the probability of capital A intersection capital C divided by the probability of C. And the probability of A given D is the probability of intersection of A with D divided by the probability of D. Okay. Also here we can see that the probability of Z given B is equal to the probability of C intersection B divided by the probability of B, which is just the probability of C over the probability of B. Why? Because C intersection B is equal to C. Similarly, we can do the same with the probability of D given B, and we obtain the probability of D divided by capital B. Now, we can write the intersection of capital A and B as intersection of capital A with C union D, which is capital A intersection capital C union capital A intersection D. So this part of here. Intersection capital C and capital A intersection D are disjoint. So the probability of capital A intersection capital B is just the probability of an intersection capital A with the union of capital D and capital C, which is just the probability of capital A intersection capital C plus capital A intersection D due to that disjoint. So we have the last formula here. Okay. And from the definition of conditional probability, we can write this equation as P, so the probability of A given B times the probability of B is equal to the probability of A given Z times the probability of Z plus the probability of A given D times the probability of D. If we divide the probability of capital B, then we get the equation shown here. Okay, so we are dividing all the elements of this first equation divided by the probability of capital B. And that becomes the probability of A given B equal to the probability of A given C times the probability of C given B plus the probability of A given D times the probability of D given B. And now let's see where we can go from there. So a very important case is when capital Z joins capital D is equal to B. And it's just the whole universe. In other words, for example, in the example of the dart could land in C or it could land in D, nowhere else, because remember, are the whole universe. You can see here that here the universe is a yellow block, and we have two elements, capital C, the circle in red, and the elements that are not in capital C is equal to D. So the union of C and D are all the universe. So if we think about the dart example, we know that the dart could land in C or it could land in D and nowhere else. And so we are asking if the dart has landed on A. So capital A intersection capital B equals capital A. So the probability of A is equals to the probability of an intersection of A with C plus the probability of intersection of capital A with D. Or we can say that the probability of capital A is the probability of capital A given C times the probability of C plus the probability of A given D times the probability of D. And now the next step is generalize this and then see what it means. So generalization is when we have many events. So all those events epsilon together, they cover the whole set, the whole universe, and they have no overlapping. And for example, we can see that here we have one event, another event, and the events are not overlapping. In this case, we can see that this arrow is this event, for example, epsilon sub index I, and this is another event, epsilon sub index J. And we can say that the event capital A is shown by this circle here. And more generally, capital A and epsilon I, epsilon 1, through epsilon subindex key are events and epsilon subindex I and epsilon subindex j are equal to 0 for all I is not equal to j. So we can say that it's an empty set for everything that is not equal to j and the union of that. And here we can see in the last part that the union of all the events epsilon is a universal set. And we typically say that since the set of epsilon subindex j is mutually exclusive and collective exhaustive. So the sum of all the probabilities, for example, the sum of all the probabilities epsilon j is equal to 1, but more importantly, the probability of capital A is the sum of the probability of capital A giving epsilon subindex j times the probability of epsilon subindex j. So here we have the same formula that we used before. And also, we can have this is illustrated in a graphic way. So if we know that epsilon subindex j has occurred, then there is a probability that capital A has occurred, which is given by the probability of capital A giving epsilon 1, epsilon 1. Also, the probability is given by the probability of capital A giving epsilon 2, and also with the probability of capital A giving epsilon 3, and so on until the last number of the epsilon subindex j. Okay, and this type of graph will appear later in the next classes when we will talk about dynamic process. Okay, so this is a graphical way. This graphic on the bottom is a graphic way of this formula of here. Okay, it's the same, but in a graphic way. So here we have an example. And also the example I think is very basic, but we show the point of this part. So let's have a set capital A, and this set capital A is the event that, for example, I will have a call tomorrow. Then we have epsilon 1, and this set says that, for example, it's raining today. We have the set epsilon 2, and this say that it is snowing today. Epsilon 3 say that it is sunny today. So let's assume that those are all possibilities and that it can only rain or can only snow, or we can have only a sunny day, okay? And not two of them at the same time. So we can have only one event and we cannot have two events at the same time. So capital A intersection event 1, we can say that says it will have a call tomorrow, event 1, event capital A, and it is raining today. So is the probability of having capital A, the probability of A giving epsilon 1, epsilon 1. So The probability of capital A given epsilon 1 is the probability I will have a call tomorrow given that it is raining today. So the event that tomorrow I have a call is the same as the event that tomorrow I have, it's the same, yeah. The event that I will have a call tomorrow is equal to the event that I will have a call tomorrow and it is raining today, union, I will have call tomorrow and it is snowing today, union, I will have a call tomorrow and it is sunny today. Remember that is all the land and that is equal to 1. So we have all the epsilons here, okay? So we can say that the probability that I will have a call tomorrow is equal to the probability that I will have a call tomorrow and it is raining today plus the probability that I will have a call tomorrow and it is snowing today plus the probability I will have a call tomorrow and it is sunny today. So the probability that I have a call tomorrow is the probability that I have a call tomorrow given that it is raining today multiplied by the probability that is raining today plus the probability I will have a call tomorrow given it is snowing today plus the probability it is snowing today times the probability it is snowing today plus probability I will have a call tomorrow given it is sunny today times the probability it is sunny today. Or in other way, the way that the formula that we saw before, we can say, for example, that the probability of capital A is the probability of capital A given epsilon 1 times the probability of epsilon 1 plus the probability of capital A given epsilon 2 plus, times the probability of epsilon 2 plus the probability of capital A given epsilon 3 times the probability of epsilon. Okay, so here we have how we can use the law of total probability. And remember that the total probability of a event are the sum of these three probabilities in this case. The next concept we have to talk about is random variables. To do that, we first let a capital V a vector space, Then we can set a random variable, capital X, and this random variable is mapping from our universe to a vector space, capital V. So X, capital X, is a function to map from one space to another space, okay? To the universe space, to a vector space that have some meaning to our solution. So if lowercase omega is an element of capital U and lowercase x is equal to uppercase x of omega, and this is part of uppercase B, then we can say that uppercase x is a random variable. Examples include the real number line, which is very often that we are going to look at. So the idea here, and also we will see another example. We will see another example in the following slides. What means a random variable? But the idea is, okay, we have a universe, and the universe has a lot of events. How to move or how to change this space to another space that represents more useful information to take into account in our problem. That is the real thing that we can do with the random variable. Okay, so one example is that capital B could be the real number line. And also, we have typical notation, as we said before in previous slide. We have typical notation, and uppercase letters, for example, capital X, are usually used for random variables. Okay, so when you see uppercase letters, remember that maybe it's a random variable. Okay, depends of the book, but usually are for random variables. And the corresponding lowercase letters, for example, lowercase x, are usually used for possible values of random variables. Okay. Random variables, for example, capital X of omega, are usually not writing as functions. The argument, for example, omega of this omega in this part is usually not right. Okay, and sometimes this can make makes confusion. So you need to have this in your mind, because some books has this interpretation and others not. Okay, now let's see one example to see what means a random variable. Okay, so now let's start with the coin flip. So our universe is heads and tails, true? Because the coin has only two sides. So the universe is capital H and capital T. So we let lowercase omega equal to uppercase H if we flip a coin and get heads, and omega is equal to capital to uppercase T if we flip a coin and get tails. Okay, so we have different events. In this case, remember that we want to move from the universe space to a vector space to take the random variables. So in this case, usually we can say that B, the vector space, be a real number line. Okay, be a real number line. And for example, here capital X of B is equal to 0, and capital X of H is equal to 1, right? And if we assume that the coin is fair, so we can 1/2 of probability to obtain head and 1 type of probability of get tails, we can say that the probability of omega is equal to T is equal to the probability that capital X is equal to 0. Okay, so we are moving from this space, the universe space where we have T and H, to this vector space, when now we are calling to T and H 0 and 1 respectively. Okay, so we can say that the probability of omega equal to T is equal to the probability of capital X equal to 0, and that is 1/2. And also the probability of omega equal to H is equal to the probability of X equal to 1, and that is equal to 1/2. This is how we changed the values from universe to the vector space. Here in this example, it's not the same always. We can make another assumption and to create the vector space. And for that, to understand that, we have another example. For example, now in this, I flip 3 coins. Okay. If I flip 3 coins, I can have 8 events, obtaining head, 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 tails, head, tails, head, head, tails, tail, tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. Okay, we can have only 8 events. Okay, so let omega, for example, head, head, head. If we flip 3 coins, I get 3 heads. Omega, another example, HHT. If we flip 3 coins, I get 2 heads and then 1 tail, and so on. Here, in this case, the other patterns, and so we have only 8 samples. Okay. The probability of lowercase omega is 1 divided by 8, because the probability of obtaining one of the sample is 1 divided by the total of samples, 1 divided by 8. And that is for all the omegas. If we say that capital X be the number of heads, if we say that capital X is the number of heads, then capital X is equal to 0, 1, 2, or 3. Not 4, not 5, not 6, not 7. Why? Because we have only 3 coins. And if we say that capital X is the number of heads, we can have 0 heads, or 1, or 2, or 3, no more. So if you can see here, now we change it from the universe space to a vector space, and now we are taking in the vector space 4 assumptions that X is equal to 0, 1, 2, or 3. So the probability of X equal to 0 is 1 divided by 8. The probability of X equal to 1 is 3 divided by 8, because having 1 head, if you come here, we have 1, 2, and 3, no more. So 3 divided by 8, the probability of X equal to 2 is equal to 3 divided by 8, and the probability to X equal to 3 is 1 divided by 8. So now we are working in the space vector. And when we are working in the space vector, now we are working with random variables. And the random variables here are the lowercase x, 0, 1, 2, and 3. So we move it from this universe to this random variables. Okay. And there are 4 distinct values of x, so the random variables. Any question about random variables, or is clear? Okay, I assume that is clear. Also, something important about probability are the probability distribution. If capital X of lowercase omega, if we say that is a random variable, then the probability that capital X of omega is equal to lowercase x is the probability distribution of uppercase X and usually written by probability of lowercase x. And for the 3 coins, in this example, the probability distribution is this. Okay, this is the probability distribution for this example of here. And also, and you can see that this probability distribution looks like this. For 0, the probability, no, also for 0 and for 3, the probability is 1 divided by 8. And here is 1 divided by 8 for both probabilities. The probability for 1 and 2 is 3 divided by 8, and it's the same here. So this is the probability distribution for this example of here. So the short way, instead of qualifying probability of x of omega is equal to x, the people often write p of lowercase x if the meaning is unambiguous. Also, important quantities related to the probability distribution are the mean and the variance, and also we can measure or we can find the standard deviation and also the coefficient of variation. When we talk about the mean it's also called average or expected value. You can see that here the mean is equal to average, or is called also expected value, this uppercase E. So we can write this also as capital E of x, and it's just the sum of x times P of x, this part of here. And we can think about the mean as indicator of where the probability of distributions lies. Also, here we have the variance here. And the variance is an indicator of how widespread or how separately the possible outcomes are. Okay? Our outcome of our function, how separately are. So then here we have a capital B sub index x, and also is writing as sigma square sub index x. And this is the expected value of x minus mu x squared, which can be writing at the sum shown here. Okay, so here we have the expected value of x minus the mu sub index a, all this square, and that is equal to this sum of here. Okay. Also have the standard deviation, and the standard deviation is the square root of the variance. You can see that here we have the square root of the variance, the capital B subindex x. And the coefficient of variation is just the ratio of the standard deviation to the mean. Okay, so here we have the standard deviation divided by the mean, by the average. And for this example, for the 3 coins example, we can say that the 3 coins, if we throw in the coins, the average number of heads is 1.5. The average number of heads is 1.5. So we have this. The variance of the number of heads is 0.75, the standard deviation is the square root of 0.75, which is 0.866. And the coefficient of variation is equal to 0.577. Something that you have to remember is that a function of a random variable, remember random variable is when we are working not in the universe space, we are working in the vector space. A function of this random variable is also a random variable. For example, a special case is the linear function, and all of us know what is a linear function. So now let's define the function, this function of here, for every omega. Okay, so we can see that this function is equal to this linear function. If we are using a linear function, we can see this result of here. And then we can measure the mean, the deviation, and other metrics that we can measure the same of here. Okay. But the important thing here that if we are working with random variables, the outcome of this function is also a random variable. And that is the importance of this slide. I think you have you have more information about Bernoulli on the videos, but we will see some small theory about that. Now we will talk about some special probability distribution. First, we will start work with discrete random variables, and we will talk about Bernoulli test. Bernoulli test has only two possible outcomes. For example, if we are talking about the coin, we can say that the outcome is equal to 1 if we obtain a heads, or 0 if we obtain a tails. Okay. For example, when we work in manufacturing systems, or we are working with machines, we can have two outcomes, for example, success or failure, if the machine is operating or if the machine is stopped because it has some maintenance or because it has some problem. But we have only two states, operating or off. Okay. The name of the Bernoulli random variable will be capital X, super index capital B, or superscript capital B, and this is, well, this is equal to 1 if outcome heads, or 0 if the outcome is 0, if tails for the before example. And then P, lowercase p, can be a real number between 0 and 1. Okay, so the probability of X subscript capital B is equal to 1, and we can say that is equal to lowercase p. Lowercase p can be some elements of p, some probability, some specific probability. So, in other hand, if capital P of X subscript B equal to 1 is equal to P, we can say that capital P, or the probability of X subscript B equal to 0, is equal to 1 minus P. Okay? So the idea here is that we have two options, success or failure. and capital X subscript capital B is a Bernoulli random variable. Okay, remember that this is a random variable. We are working here with random variables. The next one, which is based on the before Bernoulli distribution, is the binomial random variable. Suppose we throw n coins and count the number of heads we are get with those n coins. There is the binomial random variable. Then is the sum of n independent random variables with the same parameter p. Is called a lowercase, is called capital X subscript lowercase p. Okay, and here we can have the formula that defines the binomial random variable, and here in the bottom of the slide we have the probability distribution of the binomial random variable. Okay, also I think on the videos you can see this formula, and also you can see some examples. You have this presentation also in the Aula Virtual, so here you have the link to the videos, and also I uploaded some videos of YouTube with some example of how to use the binomial random variables. Here is a graph of the binomial probability distribution. Here we can see that the vertical axis is the probability, and the horizontal axis is the number of heads we get from the coins that we throw. And for this graph, we are flipping 100 coins, or we can say that we are flipping 100 coins times, a coin 100 times, and the probability of getting heads is 0.4. 0.4. This has a very important distinctive shape, because if you know, this looks like a Gaussian or normal random variable, because it has this shape of here. Here we have the geometric distribution, and this represents the number of times we have to flip a coin to get the first heads, if our example is about the coin. Okay, that how we translate this for manufacturing system. We can use the geometric distribution to know when a machine will fail. Okay, because it's the same. Here is how many throws of the coin I have to wait until I obtain heads. And if we translate the knowledge to our case, that is a manufacturing system, we can say that how many discrete times have to pass until the machine fails. Okay, so we can use this geometric distribution to know the probability of when a machine will fail. Okay, in the coin case, if the coin is skewed with probability P of coming up heads, so here is a line of what is look like, this outline, this line of here. We can see that the first time we flip a coin, and we get tails. 0, for example, here we obtain 0, 0, 0, so we obtain tails until finally here we obtain, or we get a heads. Okay, so we are measuring the geometric distribution with that. The value of this random variable is k. Okay, the value of the random value is this k of here. Okay. Formally, also, we can define the geometric random variable in this way of the button on the bottom, that capital X subscript G is equal to K if capital X subscript subindex 1 is equal to 0. Then, so the next step, the second step is equal to 0, and so on, until we obtain the geometric value equal to 1. Okay, so here we have a geometric representation of our problem. And finally, here we have the graph of the geometric probability distribution for the problem of the coin. Here we are throwing a coin, and the probability of getting a head is equal to 0.1. Okay. The vertical bars, here the vertical bars represent the probability of getting the first head on the n steps of we are flipping the coin. Okay, so in the first step, the probability is 0.1. If we throw 2 times, the probability is equal to this value here, and so on until here 35 times that we are flipping the coin. And finally, here we have the formula of the Poisson distribution. We will talk more about the Poisson distribution in the next class, but also I think I uploaded one video about Poisson distribution, and you have this video in Aula Virtual. Okay, so that is the class for today. Now we will see Aula Virtual. See Aula Virtual. And here. Okay. Today we will not have the collaborative work, so we will not have homework for this class. Okay, no, we will not have the collaborative work that usually we have within the class, during the class, because you must have to watch a lot of videos. Here you have some videos about axioms, about probability, discrete variables. Here you have some exercise about probability conditional probability. Here you have the axiom of total probability, some discrete and continuous variables, and so on. You have different videos that you have to watch. I think this Friday, the next Friday, I will upload some homework about this. And the homework will be composed by some exercise taking into account problems in flexible manufacturing systems, okay? But also taking into account all the theorems about probability. So the next Friday, I will upload the homework. So it's important watch these videos, because here you have some exercise to know how to solve the problem, okay? And that is the next class, the next week, we will have the collaborative work. And in the collaborative work of the next class, you will work with this part and also with the following part, the next part that I will upload in the following days, okay? So it's important that you watch all these videos. I know that it's a lot of information, and also some videos, the duration of some videos are 20 minutes, 50 minutes, but it's important for you watch test video, because there you have the information of how to solve. Also, Piedad, you can have one session with Piedad one Friday. I think this Friday no, but the next Friday, to how to solve different problems about flexible manufacturing system in taking into account probability. And I think someone had a question. I think was Sergio or not.
Yes, it was me, but with the comment that Piedad will give us ayudantía.
Yeah, yeah, the assistant.
It's all okay.
Yeah, this Friday no, but in 2 Fridays, Piedad will have assistant class with you. So the homework you have from this Friday, I will upload this Friday, but you will have 1 week and a half. So you have time to watch the videos, and also you will have time to assist to Piedad class, okay? And then you will have 3 more days to solve the problems, okay? That is the idea. That is the idea.
Okay. And teacher, those problems are like the videos or are like something about the something about flexible manufacturing?
Okay, are similar to the videos, to the videos, because you are seeing here talking only about probability, yeah, but maybe the videos is taking into account, I don't, I think one video he's talking about restaurants or about food. We will talk about machines, okay? So that is the only change, but how to solve the problems is the same as the videos, it's the same. Okay, any other question?
Mister, could you give us more time for the next project advance? It is for Sunday, so maybe 2 days more.
Yes, teacher, I agree with the idea of consent.
Every time you ask more time. What is this? I think this is the theoretical framework and methodology. Is this one?
Uh-huh.
Let me see. But you had a lot of time. Okay. I can do it, but the problem of this is that the qualification of this homework, if I do that, I cannot take into account in the first part of the semester. I have to take it into account in the second part of the semester, because I know that I have to upload the qualifications, I think until 21. If I have to upload until 21, I can give you time until this day, until the Tuesday. But I'm not sure. Let me see.